Here's a podcast on periodicity and atomic structure. We'll do kind of the intro notes before we start learning about electron configurations, which will not be included in this podcast. So electromagnetic radiation is light is made up of electromagnetic radiation, ER. They're waves of electric and magnetic fields that move at right angles to each other. Some examples of these waves are radio waves. Here they are on this side. Microwaves, X-rays, gamma rays. Here the gamma rays clear at the far end of the other side. And light here in the middle is the only part our eyes can detect. So this is just a tiny portion of the electromagnetic spectrum. And you notice the red end is towards the radio waves. Radio waves tend to be longer, lower frequency waves. And if you notice the violet, doesn't look so violet, does it, is toward the gamma rays end. It's not near it, but it's pointing to it. So the violet part of the rainbow that we see is the part that has a shorter wavelength and a higher frequency, so it generally has more energy. So that's what I remember. Radio waves are long and lumbering, and the violet on this side is shorter wavelengths with higher energy. So the overview, Newton separated light into a continuous spectrum, which is like the rainbow. It's like light going through a prism. White light is made up of colored light, and when you split it, it looks like a rainbow and the colors are touching one another. And then came Bunsen and Kirchhoff. They heated individual elements, for example, like ones on the periodic table, probably not all of them, until they glowed. And they passed this light through a prism, and they saw a line spectrum. They were using special stuff. I don't think they were using just their eyeballs. Anyway, they didn't see a rainbow like Newton had when he had passed it through a prism. They saw, for example, like hydrogen, they saw this color, that color, green, and this color, and the colors were all separated by dark bands. They were not blended together like a rainbow, which was kind of perplexing. Why is it not like a rainbow? Even if you just have some of the colors of the rainbow, why are they not touching? And why are the black spaces different distances from one another? So, Bunsen and Kirchhoff, their line spectrum, which was the thing we saw on the previous slide, also called atomic emission spectrum. It's bright colored lines separated by dark bands, which are black bands. The dark bands are where the energy is absorbed as an electron moves up an energy level. Energy could be energy from an outside source like electricity, maybe heat. Colored lines are where energy is released as photons as electrons move down an energy level, or maybe more than one level. Now it's called the atomic emission spectrum, or spectra perhaps. Each element has its own unique spectra. It's like a fingerprint. And it's essentially what they use when they look out at things in our universe and they don't know what it is. They can use these spectra, and it tells them what elements might be on that planet. So history of atomic models, we did this already. Dalton pretty much said that the atom is a solid sphere. J.J. Thomson, he discovered the electron. He didn't know exactly where the electrons were. He just thought they were embedded. Then Rutherford, using the gold foil experiment, proved the existence of protons and neutrons, and that's where the mass of the nucleus, the mass of the atom is. It's in the nucleus. And then came Bohr. His is the planetary model, a little bit like an onion. He studied spectra of individual elements, and electrons orbit the nucleus in fixed energy levels. He implied that the electrons do not lose energy since they do not fall into the nucleus. A photon is a tiny packet of energy, which is light. Electrons absorb energy, move to a higher energy level or levels, and then they emit photons when falling back to their ground state or the starting point. Let's just, Rutherford. So implied electrons surround nucleus and that the nucleus is positively charged. Common knowledge that opposites attract. He thought electrons collided into the nucleus. Well, if that happened, electrons would spiral into the nucleus, kind of like perhaps something falling to Earth, emitting a continuous stream of energy. And a continuous stream of energy results in a continuous spectrum, which is like the rainbow. One color blends into the next. But we don't see this when we look at the kind of light from an element. You see a light spectrum where you get colored bands separated by dark bands. So Bohr, he said electrons are in distinct energy levels. He said electrons follow Einsteinian, not Newtonian physics. It's kind of the fourth dimension versus the third dimension. He found 7 energy levels, and there's kind of the ladder or a stair analogy. You cannot be between the levels of the ladder or the stairs because the energy is quantized, but you could be on an exact rung of a ladder or a stair on a staircase. quantized. It's a discrete amount of energy that is not continuous. There is no here, it's like here or there, there's no in between. I always think of the show Bewitched when she twinkles her nose and she goes from her house to maybe her husband's office and watches him. The ground state is home versus the excited state. So ground state is where the electron starts. If it absorbs energy, it goes to the excited state, which is on a higher level, and it eventually falls back down to the ground state. So how did Bohr know electrons are in distinct energy levels? He knew this by the line spectra, so this is his proof. The band of color separated by dark bands. So if electrons fell into the nucleus, the light emitted would not be a continuous spectrum from an individual element. It would be like a rainbow, but that's not true. It looks like this when you look at it through a special instrument called a spectroscope. So today's model is called the quantum mechanical model. A quantum is the energy needed to move an electron to the next higher level. Energy levels are not equally spaced. A quantum leap, an abrupt change from one energy level to the next. Matter has a wave and particle nature, so it's fourth dimensional. We don't understand the fourth dimension, although we're made up of particles that are experiencing the fourth dimension. There's this principle called the Heisenberg uncertainty principle. We do not know the exact location or velocity of an electron, but we know its probable location. So Heisenberg uncertainty principle deals with probability. And today's model says electrons are in clouds, not in planetary orbits. So they're in spaces, and there's a probability of finding them there. So the organization of electrons. There are 7 principal energy levels on the periodic table, or there's just 7 principal energy levels. The principal energy levels are n equals 1, n equals 2, all the way through n equals 7. The larger the energy level, the greater the energy and the distance from the nucleus. So it takes greater energy to get further away from the nucleus. The maximum number of electrons on each energy level is 2n squared. For example, on the first energy level, the most electrons you could have are, you put in the energy level in for that n, which would be the first energy level. You square it, so 1 squared is 1, and times it by 2. So you can have max of 2 electrons on the first energy level. The second energy level, again, you have the 2, and then you put in 2 for the second energy level. 2 squared is 4, 4 times 2 is 8. Magic number 8. Here's the beautiful upside down building of science. And there are, how many levels in this building? I see 1, 2, 3, 4, 5, 6, 7, just like the 7 periods, but it's a little bit upside down compared to the periodic table. The periodic table goes 1 through 7 that way, but I flipped this building upside down and it goes 1 through 7 this way. And you'll notice what's interesting about this building is that it's smaller on the bottom and larger on the top. And it's a little bit as if this were the nucleus here, if you could envision this thing going all the way around in space. So this is like it's the nuke. We'll just call it like my child does. It's the nuke. And so here's like the first energy level, and it's closest to the nucleus. There's the second energy level. The second energy level has something else going on. And the third, the fourth, the fifth, the sixth, and the seventh. The seventh one is loaded. Let's see what we have next here. So the upside down energy level building. Each floor, so floor 1, 2, 3, 4, 5, 6, or 7 is an energy level. It's called the principal quantum number. Each floor has offices called sublevels. So the science term is sublevels. You could call them an office if it made you feel better. So in each sublevel has a unique shape. So these are the shapes. There's the S shape, which is a sphere. There's the P shape, which is the peanut. And there's D, which is a clover leaf. And F is flower, and they actually stand for sharp, principal, diffuse, and fundamental lines, which I'll never ask you about. So each office or sublevel has cubicles or orientations. So S has 1 cubicle, P has 3 cubicles, D has 5 cubicles, and F has 7 cubicles. And each cubicle can hold 2 electrons. So the 7 floors equal the 7 energy levels, and each floor is divided into offices or sublevels, so S, P, D, and F. And each office has cubicles. A sublevel has orbitals, or the science word for it, orientations. You can say orbitals or orientations. So S is 1 orbital or orientation, P is 3, D is 5, F is 7. Notice it goes up by odd numbers. And each cubicle has room for 2 electrons. Each orbital can hold 2 electrons. So I'm going to go back to that upside down energy level building again. So this is like the first floor, and this floor only has 1 office, which is the S office. And the second floor has 2 offices, because it's a little bigger, has the S office and the P office. And this S repeats all the way up here. S, 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 S. And the one way up here is 7. Again, I'm writing with the mouse, so it's a little difficult. And the P repeats all the way up there also. And then after, on the 3rd floor, we add another office, and it's the D office. And each floor, as we go up, also has the D office. And then when we get to the 1, 2, 3, 4th floor, we add the F. And of course, F repeats also. That's why it's called the periodic table. It's kind of this repeating pattern. And then we go to this floor, the next one is G, and then G repeats. And then we have H, and we have I. And we really only go to the Fs. We don't ever talk about those other ones. So where are these other numbers coming from that I'm talking about? So S has like 1 cubicle in it. And we represent that by 1 line. Sometimes it's a box, sometimes it's a circle. And P has 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. And then D has 5. 1, 2, 3, 4, 5. So each D has 5. 1, 2, 3, 4, 5. And then the F has 7. 1, 2, 3, 4, 5, 6, 7. So again, the 1 S has 1 orientation, so to speak. P has 3, D has 5, F has 7. And then each of these can hold electrons, so they can hold 2 electrons. This represents an electron. That's 1 electron, and then that other one's it's like a half arrow. That one's another electron. And we draw them opposite. And so here we go, we got the P. And the P, each one of those parts can hold 2 electrons, but they like to fill them up individually before they double up. It's like getting on a bus. If you get on a bus and here's the bus seat, you go, ah, I'm taking that one. The next one takes that one. Then that one. Then that one. And then that one. And then the 6th one on the bus goes, oh, I gotta share. I gotta share. It's actually a rule. It's called Hund's rule. I didn't film those other ones because I was just showing you the S, the P's, the D's, and then the F has 7 blanks, or 7 could be squares or circles, and it has a max of 14 because each one of those can hold 2. And the problem with my upside down energy level building is that it's not complex enough. Some of the floors actually overlap, and there's like little half floors in between. It sounds like Harry Potter, doesn't it? But here's a more simplified version. So we got the nucleus. And at the first energy level out from the nucleus, there's only S. And S can just hold 2 electrons. I'm going to draw an X for 2 electrons because it's easier. And then if you go to the second energy level, you go through the S's first, and then you'd go through the P's, and you have 1, 2, 3 P's, and they can hold 6. And then I'm going to erase this so I can see some. You go to the third energy level, you have your S's, and then you have your P's, and then it adds 5 D's. And then if you go out 1 more energy level, you have S's, and you have P's, and you have D's, and then we add F's. The way I remember the S, P's, D's, and F's is Seattle Police Department flatulates. Or whatever words you would like for that. But again, each one of these circles holds a max of 2 electrons. And again, if you're in the P's, you'll fill the electrons up 1 at a time. 1, 2, 3, and then you'll double them up. It's called Hund's rule. It's called the crowded bus rule. Even in the D's, you'd fill them up 1 at a time, and the F's, you'd fill them up 1 at a time. Then you go back and double them up. Because the question I'll ask you is, how many unpaired electrons are there? Let's see here. I think that's where I'll stop these notes, and I'll continue notes on a different podcast. Good luck with this.